Thank you, Mike. And hola, bonjour. Hello, everybody. My name is Jose Molina. As Mike just said, we're going to be talking about sustainability in the beverage industry. I have a couple of examples of ways that we can work with our customers in helping our customers achieve their sustainability objectives. Very quick general agenda. We are going to be talking about um, couple of different examples that we have thought that we could use to illustrate uh, some ways that we can help our customers again work on reaching their sustainability goals. So one example is on anaerobic treatment of beverage wastewater. Another example could be aerobic treatment as well. So a couple of case studies that we want to present to you as well. And then finally, there will be a short question and answers section at the end. Again, like Mike said, my contact information will be given at the end, and we'll have a few more materials available to you as well after this presentation. Once again, my name is Jose Molina. I work in business development with the ADS Systems team, which is part of Xylem. And I've been working on all kinds of biological wastewater treatment projects for all kinds of industrial customers for close to 30 years now. So I'm not an expert, but I know where to call if you have a technical question for us. I think we can try to answer and address your technical questions as we move forward. So very brief company overview about Xylem. So Xylem is a very large company. It's a recent combination of two large water companies. So Xylem and Evoqua came together about a year and a half ago, and combined we are trying to have global coverage, fairly large in terms of revenue, in terms of coverage around the world, the number of employees that work on our teams. And what we're trying to do is address our customers' needs in anything that has to do with the water cycle, whether it's on the clean water side of things or on the wastewater side, which is where I'm personally have been more involved over the years. Again, is something that we endeavor to cover for our customers around the world. Our coverage is worldwide. So I've been lucky over the years to have traveled not only all over North America, but actually around the world, different projects we chase. Where our customers go, we try to go as well, trying to address our customers' water and wastewater treatment needs. So in the title of the presentation, we have the word sustainability. That's a bit of a buzzword, but I think that's something that we've lived over the years before the word was trendy in the first place. But we realized that sustainability can mean different things to different people. So just very briefly, I'll talk about what does sustainability mean to Xylem. So it's a big part of what we do. We make sure that we have a policy that's clear about how we as a company want to do things more sustainably, but also our effect on society. We have that outward looking viewpoint where we're trying to make sure that the society itself is being protected in a sustainable way. And also we help our customers achieve their sustainability goals. So I think this chart kind of summarizes that. So we're serving our customers and we're helping our customers achieve their targets. We realize that we don't operate in a vacuum. We operate as part of a community. So there's a lot of outreach that we do to help the community around our offices or our different sites, make sure that we are always working with sustainability as part of our way of doing things. And finally, as I said before, we work with our customers in helping our customers achieve their targets as well in anything that has to do with water, wastewater, the whole water cycle. We're endeavoring to be part of that through all of our projects. Yeah. So our sustainability policy and objectives are summarized in Xylem's sustainability report. So the last version of that report came out after 2023. There is, of course, the 2024 report that will be um, released early in the new year, and you'll be able um, to read that, download it from Xylem's website. So that on the screen you see a link to where you can find our sustainability report. Okay, getting it back to our subject at hand. So our beverage customers. What does sustainability mean to our beverage industry customers? And sustainability can mean a lot of things to you as a customer. It can be about your social commitments. It can be about your production processes being more sustainable, right? Whether it's on the whole supply chain, your raw materials and feedstocks can be more sustainable. Manufacturing practices themselves can be always improved from with that objective in mind. Always looking to be more efficient in production, whether it's energy efficient, whether it's water efficient. You're as a user of clean water and a company that releases wastewater in some cases, you want to do it in a more sustainable way, a more environmentally uh, uh, responsible way with your community. So finally, one other thing we can work with our customers on is on working at reducing emissions, whether they're emissions to the atmosphere, emissions to water bodies, or even to the city sewer, and of course, reducing solid waste and material that ends up in your landfills. So all of those uh, strategies to address sustainability is something that we can work with your team on. So as I said before, we chose a couple of examples where we can help a beverage company um, achieve sustainability objectives in different ways or in different categories. So in terms of anaerobic treatment, we can discuss some of the benefits that you can get and that address your objectives. So one of them, if you're generating a wastewater that can be treated anaerobically, what you're doing is you're minimizing energy use in wastewater management. You're also, in some cases, recovering energy if you're treating a wastewater through an anaerobic process. When you do that, you're generating biogas, and that biogas can be used as a source of green energy, of course. And not only are you recovering that energy from your wastewater, but you're also reducing your use of carbon heavy fuels. So if you're using biogas, you're not buying natural gas from the grid, or you're not buying electricity that might have been generated from a coal power plant, for example. So those are different ways that anaerobic treatment can help you reduce that footprint in terms of carbon uh, released to the atmosphere. Also, if you are able to treat a waste stream or a wastewater stream anaerobically, you will tend to generate less waste material in terms of waste solids. So you're also reducing what goes out to a landfill, for example. So those are also good objectives to meet. I put this chart up here. It's just a schematic, and it gives you an illustration of what you're doing with anaerobic treatment as opposed to aerobic treatment. So if you see on the left side of this chart, just schematically, if you are trying to treat 100 kilograms of COD, of organic matter, in a wastewater stream aerobically, that means that your bacteria need oxygen to do the treatment. You have to feed that bacteria air so that they can get the oxygen from the air to do their treatment. So aerobic treatment tends to be a more energy intensive way of treating a wastewater stream. And most of that energy is being used to transform the organic matter in the wastewater into carbon dioxide. A lot of it ends up as carbon dioxide, or generating more bacteria. So as the bacteria grow, eventually you need to waste that waste material, waste sludge. And again, that's material that needs to be transported a landfill or to land application, but it does create a bit of a footprint in terms of having to manage that waste sludge. The advantage of aerobic treatment is that it does give you a clean liquid effluent, which I guess maybe that aerobic treatment will achieve some of the other objectives that you might have in terms of the water cycle. So I will talk a little bit later about an aerobic treatment example in how an aerobic treatment system can also be used to meet your objectives, but in a slightly different angle. So I'll concentrate shortly here, the next example on anaerobic treatment itself. So the chart on the right is kind of an illustration of what it is that we're doing. It's kind of like a mass balance on anaerobic treatment. So with anaerobic treatment, your bacteria can do the work in the absence of oxygen. So you do not have that need to supply that air, to supply that oxygen to the bacteria that are going to be doing your treatment. So that energy input that you had with aerobic, you will not have that energy input to treat your wastewater anaerobically. Instead, the anaerobic bacteria will take the energy itself from the food, from the organics in the waste stream, and convert most of those organics into biogas. There will also be a small amount of waste sludge. So again, in that respect, you are contributing to that reduction in pressure on landfills by creating less waste sludge that goes to disposal. One smaller disadvantage is the fact that your liquid effluent that comes out of an anaerobic reactor tends to be a little bit dirtier than aerobic treatment. So that out of that 100 kilograms of COD that you're treating, you might have still 15 kilograms of COD that needs to be further treated or further handled. But you have reduced the chunk of the organic matter. The 85% or more of that organic matter is being turned into biogas. So again, that green arrow that you see here is where most of the organics have been converted into a different form. Like that organic matter has not disappeared. It has been converted or transformed to biogas. So that biogas can then be used as a source of green energy back in production, whether it can be used in a process boiler or in a dryer back in the plant. It can also be used to generate electricity if the economics dictate that. And for the larger cases, the biogas can be cleaned as well and separated into its different components, and we can generate a renewable natural gas, which can then be put back into a pipeline. So those are examples of things that can be done with anaerobic treatment on a beverage wastewater. And again, we're trying to help our customers reach their sustainability objectives. This is a good way to do it. So a very quick example on an anaerobic system that we've done in the past few years. This is a craft brewery in the United States. They had a brand new plant that they were building in the southeast of the United States. And of course, the company had sustainability policy and sustainability objectives that they were trying to meet. They were committed to environmental stewardship, and we were very happy to work with them in helping them to achieve those goals. So expansion was part of it. So this is a medium size, I would say, a medium to large size brewery that was being built. 500,000 barrels of beer is a good production level. But they wanted to do this project and try to do it in as responsibly as possible from the environmental or sustainability point of view. They also had an interest in not just meeting their discharge requirements, but going beyond that. They wanted to exceed minimum treatment requirements. And also on the solids handling side of things, they saw that spent yeast from beer making and also spent hops represented a bit of a liability in terms of having to dispose of of those materials, and that would be a cost and also an environmental cost, right? So if you're transporting or you're trying to handle waste solids and sending them to landfill, that's not really the best way to handle those solids. So the anaerobic reactor that we designed for this customer, rather than separate and truck away, we sized the reactor such that those waste solids could be digested and also converted into biogas and into a green energy. So it's a good way to reduce the footprint, not just on the emission side of things, on the water side of things, but also in terms of reducing waste solids going to landfill. Quick numbers on what the wastewater looks like. So as you can see, the organic load in terms of pounds or kilograms of BOD or COD that are being generated in this plant and needed to be treated was fairly significant. And what we did for this customer on a design build basis was to build an anaerobic membrane bioreactor. So this is I guess, an improvement on conventional anaerobic treatment technologies, where we've added membranes as part of the treatment train, which allowed us to be able to have a very robust system, a system that can handle the solids, and a system that can transform most of that 10,000 pounds of BOD that I was talking about into biogas, rather than having to put an energy to have an energy input in terms of aerobic treatment to be able to treat that wastewater. So the concept of anaerobic membrane bioreactor is that we have the ability to make a more compact biological system, but the fact that we're using membranes to separate the treated effluent from the bacteria, it gives you a very, very high quality effluent, because the membranes that we're using to separate the liquid ensure that all of the bacteria remain in the reactor, remain in the system, and can then be used to continue to do their work, and rather than losing those bacteria into your effluent. Being able to capture the solids also means that the effluent, the treated liquid that comes out of the system, is very clean. It doesn't have any suspended solids in it, and we achieve very high COD and BOD removals through the system. So again, this is one example of where we've used flat plate membranes to do that membrane separation, to do that solids liquid separation, to get you a very clean effluent. So we think this has been a very successful example of being able to treat a fairly high organic load coming out of a beer production facility, and achieving. We're checking several boxes as we do that in terms of the sustainability objectives that are being met, not only in terms of reduction of energy being used, the quality of the water that comes out is very high, and also the reduction of waste solids that need to be handled and disposed of. So again, those are many examples of how we can do that. I should mention, as I said at the beginning of this section, is that for some of our larger projects, the amount of biogas that's being generated justifies doing the extra biogas cleaning and biogas handling. That will allow some of our customers to put that biogas, convert it to renewable natural gas. You have to separate out the carbon dioxide and some other impurities, but you can then put the biogas into a pipeline and get, there's plenty of incentives out there. And we'll be happy to talk to you about your particular needs to see if generating RNG, right, renewable natural gas, is a good option for your facility. Okay, so getting back to aerobic treatment, anaerobic is a good way to achieve some sustainability objectives. When you do aerobic treatment, there's also a series of objectives that can be met. by doing that design, doing it right, and applying the right technologies to help you achieve your treatment objectives. So I'll go back to that chart I showed before in comparing anaerobic treatment to aerobic treatment. But if we focus on the left side of that chart, as I said before, there is an energy input to doing treatment aerobically, but you can do it efficiently or less efficiently. So that's one thing that we can work with your team is to make sure that the design of an aerobic treatment system is done with sustainability in mind, and we make sure that we have as efficient an aeration system as we can, that the equipment, pumps, mixers that we use in our treatment train are being selected with the sustainability, with the energy efficiency in mind, so that we can continue to help you achieve those objectives. But also, as I was saying earlier, where the quality of the water that comes out of an aerobic treatment system can be high enough that then you can maybe achieve different kinds of objectives on the sustainability side. Having a clean treated wastewater means that maybe it opens doors to water reuse, for example, or being able to meet emissions to water bodies and discharge water that's much cleaner and cleaner for the environment, and you can meet that your direct discharge limits that, as you all know, are getting tighter and tighter with time. So we have more strict right now. Discharge into a stream, it's getting harder to do that. From the point of view of phosphorus, nitrogen, and even the BOD and other parameters, they need to the objectives for discharge are getting stricter or tighter as we move forward in time. So a quick example of a project that we've done in the recent past on the aerobic MBR side of things, so aerobic treatment achieving a fairly high quality, is a beverage plant in the US again, where the plant was being asked to meet a more stringent BOD, nitrogen, and especially phosphorus objective for discharge. So the solution consisted of, again, membrane bioreactor. In this case, it's an aerobic membrane bioreactor, but it's a similar concept to the one I described with the anaerobic system. Just very quickly, what is an MBR? So a membrane bioreactor is a variation or an improvement on a more conventional activated sludge process. So as you know, with activated sludge, you're using a consortium of bacteria aerobically. So you're adding air to those bacteria so they can do the work. And as the bacteria receive air and food, they can do that conversion and cleaning of the water so that you can reduce the organic matter that goes out to your final effluent. Typically, the design of an activated sludge system is based on how much bacteria, how much of a biomass, or how many bacteria, how many workers you have to do the treatment, and that's limited by volume. So the larger the system, the more bacteria, the more workers you have, the more wastewater load that you can clean. So of course that means that you need a lot of space to do your biological treatment. Another bottleneck in the design of conventional activated sludge systems is the fact that you have to separate treated effluent from the bacteria because you want to keep the bacteria in the system. So normally, a conventional treatment train requires gravity settling. So your bacteria settle to the bottom in a secondary clarifier so they can be returned to the main treatment train, and then you release clarified effluent. So the bacteria stay, clean liquid goes out to discharge. But again, that's another bottleneck because we have to rely on the fact that bacteria settles slowly in order to give you a clean effluent. When you combine membranes to the treatment train, you can eliminate the need for a secondary clarifier. You can eliminate the need for the bacteria to settle out. So instead of the bacteria settling out by gravity and then decanting that off, that clear liquid on the top, using membranes means that you don't have to wait for that bacteria to settle out. You can actually separate it physically because the bacteria cannot get through the pores of the membrane. So that allows you to have a much higher concentration of workers, and it also allows you to reduce the amount of volume that you need for treatment. So typically you can reduce an MBR system can be maybe a quarter or a third of the volume that you would have on a conventional system. So again, that also can reduce your physical footprint of your treatment system. Again, those are huge benefits that you can get by doing that. And of course, the fact that the membranes are capturing all of the solids in your final effluent, it means that the water has a much higher quality because there are no solids in it. Very low BOD, the level of BOD removal that you get is much higher than you have in a conventional system. So that means again you're checking off more boxes from the sustainability side of things. So I showed this graph before again. So this example that I'm talking about was based on flat sheet membranes. So again, what you see, the cassette that you see on the top right, is a series of membranes that are in a rectangular flat sheet. Liquid remains in the reactor, and mixed liquor, the sludge remains in the reactor, and clear liquid goes through the membrane pores. We use air that we bubble in through the bottom of that membrane cassette, and as the air bubbles rise in the liquid, they actually create this scour effect that keeps the membranes clean. And again, you get a cross flow effect, so the clean effluent goes through, and the sludge keeps getting recirculated inside of the reactor. Here's a picture of what membrane tank looks like. So inside of this tank at the top, the picture at the top is with the aeration turned off, just so that you can see what it looks like. But once the system starts operating, it looks like the picture on the right, on the bottom. I mean, so again, as you see, this is a very highly concentrated sludge. So there's a lot of bacteria in this tank. And as the liquid goes through the membrane pore size, which is very small, 0.2 to 0.4 microns, then what you have going through is a treated effluent with no suspended solids in it, and very high removal of nitrogen, phosphorus, and BOD. So this is a wastewater, with still quite concentrated, maybe not strong enough to justify anaerobic treatment. But again, we are chasing other sustainability objectives in a different way. So it's aerobic treatment. It's not as energy efficient as anaerobic treatment, but we can still do it as efficiently as possible and actually meeting other objectives. For example, having a water that's so clean that maybe it can be reused back in the process. Just some illustration of what the system looks like. So what the picture that you saw before from the top, this is what it looks like looking at it from the side. So on the left is the membrane tank. So the cassettes are housed inside of that tank. And we're using the blowers on the right to blow that air into the bottom of the reactor so that the bubbles, so that as they rise, will keep the membranes clean. So as I said before, the air keeps the membranes from getting plugged up with the sludge, so that the air creates a cross flow that cleans the water. But still, every few weeks or every few months, you might do a clean in place. You don't have to take the system down. You actually just stop flow for 2 or 3 hours, and you actually can do a clean in place with chemical, whether it's an acid clean or a hypochlorite clean. It's just done from time to time just to remove material that might have started to get stuck on the little pores on the membrane. The system creates, as I said before, a very clean effluent. So as you see, the blue dots on this graph are COD concentrations coming in, quite variable. And what you see with the orange at the bottom is shows you how clean that wastewater can be and how steady coming out of the reactor. It bottoms out, in the 98, 99% COD removal. So COD, the organic matter in the final effluent, is very clean and always very clean. Likewise, we were able to meet the total nitrogen limits that had been imposed, and as well as the phosphorus limits. So with phosphorus, we know that we're removing some of the phosphorus biologically because the bacteria, as they grow, they will absorb some of that phosphorus in terms of for meeting their growth needs. But there will be an additional phosphorus removal step by adding a coagulant, whether it's a ferric chloride or alum, to precipitate it out with the phosphorus. The great thing about a membrane bioreactor is the fact that now you have, once you've created that chemical precipitated sludge of aluminum phosphate or ferric phosphate, we can capture those solids because we have the membranes that are keeping those solids from going out in your effluent. So having no suspended chemical sludge and the bacteria also are staying in the reactor, that means that we can meet less than 1 ppm phosphorus limits. In some cases, we can go as little, and we can remove another order of magnitude and meet quality more in the range of 0.1 or even less milligrams per liter of total phosphorus. Same thing for total suspended solids. I've made this point a few times already. The concentration of suspended solids in that final effluent is non-detect because by definition, the pore of the membrane is capturing all of the suspended solids that are in the system, so nothing can get through the membranes. Just very quick summary of performance of the system. As you can see, there's still a little bit of organic matter in the wastewater that maybe is not degradable, so 30 ppm of COD, but the BOD is non-detect in this system. So we were achieving 99.9% BOD removal. TSS is practically all removed, and we're also meeting at we're achieving 0.6 milligrams per liter of total phosphorus in your final effluent. So again, it's very, very clean water. The additional point that I was making earlier about making water aerobically this clean is the fact that now you can see if there are other objectives that you can meet on the production side of things. Can you be more water efficient? Yes, overall for the production plant, you can be more efficient if maybe some of this water can be used back in the process in some way or another, and that reduces your consumption of city water or well water that you might be bringing into the plant. So again, that really helps you achieve maybe objectives that you might have in terms of water use in production as well. And finally, in some cases, that water can be fully recycled if, for example, you were to feed that treated wastewater through an MBR system. You can feed it to something like a reverse osmosis system, and that can give you ultra pure water that maybe you can even close more loops in terms of water consumption back in production. So those are just some examples that I wanted to touch on in terms of examples of how you can use wastewater treatment to design properly to help achieve your sustainability objectives in production. And this is just a summary of results. Again, we're very happy to look at each specific plant. If you have specific needs on the water and wastewater side, we're always happy to work with teams and seeing how many of those sustainability boxes we can help you to achieve. Um, that was a bit of a discussion, more of a planting of ideas, I thought. I'd be happy to answer questions, or as a follow up in the future, feel free to reach out to me and we can look at your plant specific needs and what your wastewater looks like, what your objectives might be. And we'd be happy to put in front of you one or two or maybe more options on how you can we can help you achieve those sustainability objectives. With that, Mike, I pass the floor back to you. Thank you.
Yeah, thank you, Jose. That was awesome. I released another poll, the facility I represent. Just curious to know like kind of where you guys are in your journey. We have some people who are just starting out with the research. I'll share the result. We had some people join a little later, so I'm going to just release the other poll too because I'm kind of interested to see how that works. So I'm going to share this first poll if I can. Maybe I can't. I guess I can't. One of the questions is, what is the range of capital investments for these systems?
Yeah, that's an excellent question. Of course, as you might know, the capital cost of wastewater treatment is directly proportional, not necessarily just the flow that you're generating, but also the amount of organic load that you need to treat. So some of the systems that we've done in terms of capital costs, they can be from $500,000 to 20, 30, $40 million. But it really depends on the magnitude of the load that you're trying to treat and the flow that you're trying to treat. And again, the cleaner that your effluent needs to be also might affect how much of an investment a system like this will take. Um, it's a case by case uh, issue here where we would be happy to look at your specific needs, your specific flow and wastewater characteristics, your specific objectives, and we can definitely come up with an estimate of what it would take to treat. Of course, we know that financial pressures are never to be ignored, and so what we want to present to you would be something that makes sense financially, something that has a payback of some sort, whether it's payback on the anaerobic side by getting some value out of the biogas that you generate, or you can also look at how much does that clean water represent in terms of value if you are able to reduce your water consumption. Sometimes it's a little bit more intangible, right? Because you're trying to meet sustainability objectives, but always a company needs to have the bottom line in mind. So yeah, definitely something that you will have to look at the payback of whatever treatment train we propose to you, for sure.
Here's a question that kind of dovetails into that, and maybe this relates in a way. Does the size of your brewery or distillery matter if you want to generate biogas? So rather than asking for the cost of capital investment,
Mhm.
what is the size of a facility where you could start this process? In other words, can you be a small distiller brewer
Yeah.
and then start thinking about this, or do you have to be a larger one?
Yeah, that's an excellent question. So there, on the anaerobic side of things, I think the larger the plant and the higher the concentration of organics, the more it goes towards anaerobic treatment. Um, but as the systems get smaller, maybe there is a point where even if the wastewater is high strength, the capital cost is not really justifiable, and then we might look at maybe aerobic treatment, and then maybe helping you meet other objectives, sustainability objectives through aerobic, but maybe not meet as many if you're not doing anaerobic treatment. I would say that the small craft brewery plants, we would have to look at it case by case. The medium-sized ones, I can't remember the number of barrels that per day, 300,000 barrels, I think is what that we were looking at for that example. it would be maybe a third of that, so 100,000 barrel production would be something that we definitely would be looking at anaerobic treatment as a good option. Yeah, but medium-sized craft breweries or beverage plants, we would start to look at having something on site. Again, it's case by case because depending on what kind of uh, costs you're already incurring by sending your raw wastewater to a municipal plant, for example, then you have to look at you save on your sewer bill, but then you have to invest in treatment. So that's a whole decision matrix that would come into play, and as to where it makes sense. At what point does it make sense to have an on-site wastewater plant?